Hello everybody, this is John Buck. I'm back with another in my array signal processing series, and this video we're going to talk about array gain for the case when we have background noise that is not white noise but more complicated, particularly the case ultimately of an interferer. And we're going to compare the array gain we get from a conventional beamformer with the Capon minimum variance distortionless response beamformer. So we're going to set this up in the framework of a hypothesis test that we talked about earlier, except are going to have a slightly different hypothesis test. Our null case now is going to be the case where we assume we've got not just background white noise, but also an active interferer. So that this part N would be the white noise we saw earlier. So we'd say this is a complex Gaussian with zero mean and a variance sigma n squared I. So this diagonal covariant spatial covariance matrix tells us it's independent. Whereas this part here is the interferer, where it has, we'll assume V1 is a fixed direction, the manifold vector for the fixed direction that is coming from. But A1 is a scalar complex normal, is the varying amplitude, the random amplitude of that interferer that will change with time. But we'll say it has some power sigma 1 squared. Okay, so this is the background we're dealing with all the time. And we're also going to assume then that in terms of the Capon case, that Sn is the spatial covariance when the background is we could say this is the conditional expectation of XX Hermitian conditioned on H naught. Right, so this is the signal absent spatial covariance matrix is what we use for Sn. And we can show for this particular case, I mean MBDR doesn't assume this, but this is just sort of the simplest interesting case to look at with MBDR, that if we plug in for XX Hermitian and bring the expectations inside, we'll end up with sigma 1 squared times V1 Hermitian plus sigma n squared times I. And we saw this similarly in the last week with the generalized side lobe canceller video. And then for H1, we're going to add another term in, right? This second term is the signal. Right, and we're going to assume for this that V naught is the fixed manifold. Should have made it clear that this is fixed. So the V1 is not random, but A1 is a random amplitude for the V1, the direction represented by the V1 manifold vector. Similarly here, AS will be random. This will be the signal power, so it's a random amplitude. Let's say complex Gaussian, and we'll call this, say, sigma S squared. Okay, so if we want to find the array gain, we want to say we're going to look at a beamformer. We're going to say if I want to find an array gain, I'm going to need a beamformer. I want to sort of do before and after. We say what's the impact of processing with this beamformer? How much do I gain by the array? That's why it's called the array gain. So if we want to compute this, good to sort of review and refresh in your mind. So I want you to think for a second, remember what's the definition of array gain. Challenge yourself to remember that. Pause the video and think for a second. And then see if you can come up with it and then come back and I will tell you. Okay, so we're back now. And again, what array gain is it's the ratio of the, we'll say array gain is the signal to noise ratio at the output of the beamformer divided by the input. So that's the equation. Conceptually, what is it telling us? It's telling us how much better is the output, how much better is the signal we were using at the output than it was at the input. Right, so if we wanted to write these out, we could say, I'm going to move them over here, or maybe move up a little bit. Right, we could say, well, SNR out would be, if we call this part here, we could call this X sub S. For the signal part, it would be the expected power using superposition. We'll break X into two parts, right? The signal part over the noise part, which would be the Sn up above. And so if we wrote that out and took its expected value, I've already brought the expected value inside here, so sort of got things out of order. So let me not get too far ahead of myself like that. So we'd say this would be the expected value if we're going to keep it the same as we had in the numerator of the power of W Hermitian squared with the X And this we'd say this is the I plus N, interferer plus noise part. So everything else that isn't signal. And now we could bring this through and say, well, this would be the expected value, if I break it down a little more, of this x sig would be A times V naught. So I'll bring the A sig out front and I'll have W Hermitian V naught. I can bring that A sig out front because it's a scalar. So I can just pull it out to the front. So I have the expected value of that squared. And in the denominator, this would be W Hermitian X times its conjugate, and bring the expected value inside. And we're left with W Hermitian SNW. And now I look at this numerator and say, W Hermitian V naught, well, that's going to be equal to 1 because of the unity gain constraint. So I've got the expected value of A of S magnitude squared. Well, that's my sigma S squared up here. So I end up with sigma S squared over W Hermitian SNW. And we'll leave that be for now and think about the input. We say, well, what's the input SNR? Right, because we need that denominator for the array gain. Well, the numerator would be the same, right? All the sensors would have the same. We could talk about the average power, but again, the numerator, the signal part, could be, well, we could say it this way. It's going to be the average power for the signal part outer product with itself. Or now, well, let's do it this way. The magnitude squared of the signal part, which will give me 1 over n, and this would be the trace of x sig times its Hermitian, right? That way, each element on the trace is the sum of the diagonal of a matrix. And so if I take x outer product with itself, the diagonal of that matrix will be the magnitude squared of each sensor, and then I need the expected value of this. So there's an E in here. So the expected value of that, but for each of those we saw above, that's the sigma S squared. So this would give us 1 over n times the trace would be, each term on the diagonal would be sigma S squared. And so those would cancel out, and I'd be left with the ends cancel out. And I'm left with sigma S squared. Again, so that makes sense. It's the same average input power for the numerator. That's for the numerator. Then the denominator would turn out to be the same approach with this trace. I can say this is 1 over n times the trace of sigma S sub n. Right, so this, because on the diagonal of this matrix is the power at each sensor. So the trace is the sum of those, and I divide by n. So this altogether is giving me the average noise and interferer power at each sensor. The average over the sensors. Right now, if they're all plane waves and white noise, they all work out the same. And so in this case, this denominator becomes 1 over n times, well, the trace is the same for each of them, and I get sigma 1 squared plus sigma n squared for each of the n elements on the diagonal. Right, if I go up here, we can see that. Right, that each of these on the diagonal, each of these V1, V Hermitian, the exponentials cancel out, and I get 1. So on the diagonal, I always have sigma 1 squared and sigma n squared. And so again, the n's here cancel out. And what I end up with left is sigma 1 squared plus sigma n squared in this case. And more generally, even without assuming this, we're going to call this sigma naught squared. Would be the average. So if we don't want to assume we have white noise or we don't know how many plane waves there are, we're just saying if I took the spatial covariance matrix for the signal absent data, took the sum down the diagonal divided by n, that would be the average power I was seeing across the array at a single sensor for the noise and interferers. Okay, so this is my input here, and then to get to an array gain, I'm going to need to do one more piece, and then we'll go on to the next video, which is, I realize now I'm going to have this, if I write it this way, I'm going to have the denominator input S and R we call sigma S squared over sigma naught squared, right? This is the average input power. So this is the S and R at the input. We need to, looking ahead, we're going to divide this type of expression by this type of expression. We're going to need to get rid of this sigma naught. So we're going to write S of n as a factored into two terms, one of which is the average power at the sensors, and the other contains the spatial structure. So we're going to say we're going to create something called S bar of n is going to be our average power, or sort of our spatial average. I'm going to say that is going to be equal to, if we take the full covariance matrix and divide it by sigma naught squared. So we average out the power, and so this is about the spatial structure of the noise. Sn bar is about the spatial structure of the noise if we sort of normalize by the average power. So one of the consequences of this is that the trace of Sn will always be n, the number of elements in the array. And so it's sort of capturing, it's always got the same scale factor there, and it's bringing that out. And that will be handy, sort of looking ahead, we can see if I bring that up here. Right, so if I take this factorization and put it in up here, I can pull the I can have sigma naught squared times Sn. And I can pull that sigma naught squared out front. And so I'll have W Hermitian times the Sn bar, the normalized spatial covariance of the noise and interference, times W. And so looking ahead, I can see when I go to compute the array gain, I'll have something that looks like this. All right, so if I do that, in fact, maybe I'll do that, I can do that in general. Well, let me write that down, and then that's a good stopping point before we go to the next video. So based on all that, the array gain for any of these cases, I'll have, now I have sigma S squared over sigma naught squared times W Hermitian S n bar W over the input SNR, which I'm going to write as multiplying by the reciprocal. Right, so this sigma naught squared over sigma S squared, right, that is the bringing this down and turning it into a reciprocal, because it was going to be in the denominator of the array gain, right? SNR in is the denominator of the array gain, so it's like multiplying by the reciprocal of this. And the reason we did that normalization now becomes clear, as I end up canceling these terms. And what I'm left with is W Hermitian Sn bar W. For any beamformer, this is my array gain. So it has to do with we've seen already, in the simplest case, for white noise, Sn bar would just be I. It would be the identity matrix, and this gives me 1 over W squared, magnitude W squared, which is a good sanity check. All right, so I'll stop this video here. In the next video, we'll pick up and look at what happens with this when I look at a CBF, or if I look at a MBDR beamformer. Okay, I'll see you next time.